Very good evening, everyone. So, as you all know, that today we will going to continue with our chapter 2, Electrochemistry, theory part 6. So, today is the part 6 of the theory of electrochemistry. Okay, so we are going to see the NCERT chapter 2, Electrochemistry theory part 6. Let's start. Disclaimer: the images, text, and other materials used in our presentations are for educational purposes only. We respect the intellectual property rights of original creators and owners. If you are the owner and have any concerns or issues, please contact us at sathi@iitk.ecu.in and we shall remove the content immediately. Please note that parts of the content may have been generated using the generative AI, which is experimental. So, today's objective of this class is that after studying this lecture, you will be able to understand the quantitative aspects of electrolysis. So, the topics to be covered as per the NCERT are the first of all, we will cover our section 2.5, which is electrolytic cells and electrolysis, under which we will cover first of all the electrolysis, then quantitative aspects of electrolysis. Then we will see that what is the Faraday's first law of electrolysis given by the Faraday. Then electrochemical equivalence. Then we will talk about the Faraday's formulation of first law. So Faraday's first law formulation. And then we will talk about the Faraday's second law. And then illustration of Faraday's second law, we will study in broad that what is the second law given by the Faraday. And then we will also cover the subsection 2.5.1, which is products of electrolysis, which comes under the section 2.5. And later we cover some example, which is 2.10, marked as 2.10 in our NCERT textbook. And then we will talk about the in-text questions. So we will see some in-text question and solve them from 2.10 to 2.12 as per the NCERT. So let's start with the first topic, which is electrolysis. Okay. So electrolysis is a chemical process that uses an electric current to drive a non-spontaneous reaction. Okay, so electrolysis is a chemical process which use an electric current to drive a non-spontaneous reaction. So non-spontaneous reaction means there are two kind of reaction, spontaneous one and the non-spontaneous one. Spontaneous one mean the reaction can happen spontaneously, like if you talk about the delta G for that reaction, that will be marked as less than 0. But if the reaction is non-spontaneous, then del G, Gibbs free energy, is greater than 0 for that reaction. Okay, so electrolysis is referred to the process or the chemical process which will use the electric current. So basically it is a chemical process, but it will use the electric current to derive the to drive the non-spontaneous reaction, to make happen the non-spontaneous reaction. In an electrolytic cell, okay, now again we are talking about the electrolytic cell. Electrolytic cell means we have electrolytes in our cell, including different ions like copper, zinc, right, aluminium. So in an electrolytic cell, the external source of voltage is used to bring about a chemical reaction. So if we talk about the electrolytic cell, where the two electrodes are present, a electrolytic solution are present in which our electrodes are dipped, and the two electrodes are connecting with the wire through which the electrons and the current is flowing. So in the electrolytic cell, external source of voltage, that means you have to provide a current, you have to provide a voltage through, you can say, an instrument. So you have to provide a external source of voltage. That means you have to provide the voltage externally to this battery or to the cell to bring about a chemical reaction, for happening a chemical reaction, for happening of a chemical reaction inside the cell. One of the simplest electrolytic cell consists of two copper strips dipping in an aqueous solution of copper sulfate. Okay, one of the simplest electrolytic cells. So if you are taking, if you are supposing an electrolytic cell here, which is, let's suppose the simplest electrolytic cell, which is consisting of two copper strips. It is having two copper strips. Strips is basically a small width and long length papers or sheets of the copper. Okay, so two copper strips dipping in an aqueous solution of copper sulfate. Now it is dipping in the copper sulfate solution, and the metal which is made up of the strips, like strip is made up of copper, and copper strips are dipping in the copper sulfate solution, Cu2SO4. Now, if a direct current, DC represents direct current. So, if a direct current voltage is applied to the two electrodes, then the copper is converted into the copper 2 plus ions. That means the metal will convert to the ion at the anode by the reaction copper giving us copper 2 plus 2 electrons. That means the oxidation reaction which is happening at the anode of the cell. Okay, if a direct current voltage is applying to the two electrodes, as I said that we are supposing a simplest electrolytic cell in which we are taking two copper strips, in which one of the strip will act as anode and the another will act as cathode. So these two strips dipping in the aqueous solution of copper sulfate. So it is the simple representation of a cell where we have a solution where two electrodes are dipped into it, and they are connecting by some wire, and through this we have to apply external voltage. So here we are saying that if a DC voltage, direct current voltage, we are applying to the cell or to the two electrode, that means if we connect a DC voltage to this wire, then the copper is converted into the copper 2 plus, then copper metal solid state will convert to the copper 2 plus in the ions in the aqueous form at the anode by the reaction. At the anode, this reaction will happen. Okay, now this reaction is actually NCERT equation marked as 2.29 in our electrochemistry chapter in the NCERT textbook. So further, if you talk about this, then copper metal is deposited on the cathode and the following reaction takes place. Now, if we talk about the cathode, at the cathode, this reaction is taking place where the copper 2 plus ions is gaining or adding 2 electrons to itself and converting to the copper in the solid state. Okay, so copper ions is converting into the metal. So 2 positive is converting to the 0 state, that is neutral state. Okay, so copper metal is depositing on the cathode following this reaction at the cathode, and this is NCERT equation marked as 2.28. Now this is the diagram. If you see, we have a container here. Okay, we are calling it here as tank. Okay, so in the tank, these are the two acidified copper sulfate. So okay, so the blue color solution is acidified copper sulfate solution, CuSO4. Okay, so copper sulfate solution, and this is anode. This one is anode, the right one electrode, and the left electrode is the cathode one. At the anode, the oxidation process is happening with the reaction of Cu going to Cu2 plus 2 electron, right? And at the cathode, what is the reaction which is happening? It is given by this Cu2 plus 2 electron. This will give you copper. Okay, so at the anode, this reaction is happening, and at the cathode, this reaction is happening. Now you can see that both the electrode are connecting through the wire where a key is attached and a voltage is attached. In this direction, electrons are flowing. Okay, you can see. Okay, and when you close this key, the current will flow through this wire, and a DC voltage will apply to this two electrode system. And the impurities, that means which we are calling as anode mud, by the oxidation of copper, which is happening at the anode. So this is kind of depositing at the bottom of the tank, and here the copper 2 positive is releasing from the anode after the oxidation process, and the copper 2 plus ion is deposited over the cathode by the reduction process. Okay, so this is the diagram for the simplest copper cell, which we are taking as an example here. Now let's talk about the quantitative aspects of electrolysis. So Michael Faraday, on the basis of his research, investigated the electrolysis quantitatively. He found that during the electrolysis process, the quantities of the substances liberated at the electrodes depend upon the following three factors. Okay, so basically, he doing his research, he investigated the electrolysis quantitatively, and what he found that during the electrolysis process, quantities that are liberated at the electrodes, that means cathodes and anodes, during the electrolysis process, this is depending upon the following three factors. The first one is the quantity of current passed. Okay, so how much the substance is liberated at the electrode in our cell is depending upon the factor that what's the quantity of the current which we are passing through the cell, for the working of the cell, for the functioning of the cell. Second factor is the time duration of passing the current at a uniform rate. Okay, uniform rate means that if you are starting with the passing the current at 2 ampere per second. Okay, ampere is a unit we use to measure the current, electric current. Okay, so if you are using 2 ampere current per second, then uniform rate means that from the starting of the closing of the key in the wire to the opening of the key in the wire, this is the same amount of current which is flowing through our wire. Okay, not above it, and not below it, like not even 3 ampere, not even 1 ampere, only 2 ampere per second is flowing through our wire of the cell. So what is the time duration of that passing of the current at that uniform rate, that how much time duration you are taking for passing of that current into the wire. Okay, like how much our cell is functioning basically. So this is also a factor which affects the liberation of the substances present in our cell at the electrodes. The third factor is charge on the ions being deposited. Now the ions which are deposited over the electrodes, okay, two electrodes are present, one cathode, one anode. So what is the charge which is depositing on the electrodes? Okay, that will also affect the liberation of the substance at the electrode. Okay, so these are the three factors as per the Michael Faraday research or investigation. Now, Faraday gives his first law of electrolysis. So this first law of electrolysis was given by the Faradays, as the name says. Now, it says that the mass of an element liberated on an electrode during the electrolysis process is directly proportional to the quantity of the electricity Q which passes through the solution of an electrolyte. Okay, so what he says in his first law, that the mass of an element which is liberated on an electrode, basically we have this structure where the two electrodes are present, right, and we have a solution in which they are dipping, and the copper ion is eliminating or releasing from this anode 2 plus, and from the cathode the copper ion is inserting inside it or depositing on the cathode, right, and they are connecting through the wire through which the current is flowing, right. So what the law is saying, that the mass of an element liberated on electron. Now what is the mass of the element which is depositing over the electrode, here in this case cathode? That mass, and during the electrolysis process, okay, during the electrolysis process, whatever is the mass of the element which is liberating at the electrode is directly proportional to the quantity of the electricity you are providing to the electrodes, that which is representing here as Q, which passes through the solution of an electrolyte through this wire. Okay, this is the thing which is the first law of electrolysis is saying. So if M is the mass or the amount of a substance deposited or liberated, and I is the current in the amperes which passes for the t amount of seconds, then according to the law. Okay, so we are explaining the first law statement. So if you take M as a mass or the amount of a substance which is deposited over the electrode or liberated from the electrode, and I is the current in the amperes unit which is passing for this much of seconds, t seconds, let's suppose, then according to the Faraday's first law of electrolysis, the M is directly proportional to the I times t, the current times the time in the seconds. Okay, like time for which the current is passing in the wire or in the circuit, right? I into t is basically Q, that is charge. Okay, as in the statement says that the quantity or the mass of the element which is liberated on the electrode during the electrolysis is directly proportional to the quantity of electricity, that means the charge. Okay, the Q, and Q is equals to I times t, current multiplied by time. So mass is directly because mass is directly proportional to Q, as I said, that means mass, as Q is equals to I times t, then mass will be directly proportional to I times t, right? Now when you remove this proportionality sign, there will be an equal to and a constant. So, or what you can say, that M equals to ZIT. Now Z here is a constant, I is the same as current, and T is the same as time in the seconds for which the current is flowing. Where Z, now what is it? Z is a constant which is called electrochemical equivalent of the substance. Okay, so here we introduce a constant which is called as electrochemical equivalent from the first law of electrolysis. So according to the statement of the first law of electrolysis of Faraday's, this is the equation for it. M equals to ZIT. Now let's talk about electrochemical equivalence. So if 1 ampere of current is passed for 1 second, that is 1 second, time equals to 1 second, I equals to 1 ampere. Okay, then M equals to Z, right? Because M equals to Z times I times T. Z is a electrochemical equivalent, I is a current, and T is a time. If 1 ampere of current, that means current will be 1, is passed for 1 second, time is 1, then M equals to Z. 1 times 1 will be 1 and Z times 1 will be Z. So M will be equals to Z. Okay, as written here. That means, this means when 1 ampere of the current is passed for 1 second, then the mass or the amount of the substance deposited or liberated is exactly equal to its electrochemical equivalent. Okay, this is what it is saying, that if you are using 1 ampere of current which is passing for 1 second, that means that mass which is liberating or depositing on the electrode, that mass is exactly equal to the electrochemical equivalent of the substance, that is Z. Okay, so it is given by the formula Z equals to, that is electrochemical equivalent equals to molar mass of the metal divided by the charge on the cation part multiplied by F, that is Faraday's constant. Okay, so this is the formula which we can use for the electrochemical equivalent, that is Z. Now let's talk about the formulation of Faraday's first law in detail. So the mass of any substance deposited or liberated at an electrode is precisely proportional to the quantity of electricity carried through the electrolyte, according to the Faraday's first law of electrolysis, solution or melt. Okay, so this was the statement given by the Faraday's first law of electrolysis, right? We just have studied that the mass of any substance which is deposited means deposited over the electrode, or liberated means exiting out from the electrode. So deposited or liberated at an electrode is precisely proportional. Precisely means exactly, near to exactly, proportional to quantity of the electricity carried through the electrolyte. Okay, what is the quantity of the electricity which is electrolyte is carrying, which is electrolyte is having? So this was the statement given by the Faraday in his first law of electrolysis. So if let's suppose m gram of substance, that means mass, we have given the mass. So m gram of the substance is deposited when q coulombs of electricity are passed through it. Okay, so q, as I said, q was charge. Q is charge. Okay, charge is basically the quantity of electricity. So q is charge, and charge unit, we use the unit coulomb to measure the charge. Okay, coulomb, representation by capital C. So if you have a m gram of the substance, small m gram of the substance, which is deposited when the q amount of electricity are passed through it, then m will be equals to zq, because m equals to z times I times t, and I times t is basically q, so m equals to z times q, right? So m equals to zq. The electrochemical equivalent of the deposited material is the z. Okay, so now the m gram of substance which is depositing, having the electrochemical equivalent as z, which is proportionality constant here in this equation. Now if a current of 1 ampere is passed for t seconds, okay, for t seconds 1 ampere current passed, then m or you can say charge is equals to current into time. This we know that q, that is charge, equals to current. Current means I multiplied by time, time means small t. So q is equals to it. We know that q equals to it. And if the 1 ampere of the current is passed for t amount of second, that means I is 1, then q will become equals to t, and you can put it here as m equals to zt. Okay. So let's talk about the Faraday's second law. Faraday's second law of electrolysis states that mass of a substance deposited at any electrode on passing a certain amount of charge is directly proportional to its chemical equivalent weight. So in the first law, he's saying that the mass was directly proportional to the amount of electricity passing through the circuit or passing through the wire, or providing to our cell. But in his second law, he states that, or Faraday's second law of electrolysis states that the mass of a substance which is deposited at any electrode in our cell on passing a certain amount of charge, that means we have in this law we have a known charge which we are passing on the cell. So the mass of a substance deposited is directly proportional to its chemical equivalent weight. Okay, it means substance weight. Okay, substance chemical equivalent weight. Or what are the other definition? That when the same quantity of electricity is passed through several electrolytes, the mass of the substance deposited are proportional to their respective chemical equivalent or equivalent weights. Right? So if you are using a same quantity of electricity, okay, either in one cell or two cell or more cells, So if you are using the same quantity of electricity to pass through several electrolytes, that means we have a different solutions, different cells through which you are passing same quantity of electricity, then the mass of the substances, so let's suppose we have three cells. One cell having two electrodes, second cell having again two electrodes. So this is first cell, this is second cell, and let's suppose this is third structure which is again having two electrodes. Okay, now if the electrolysis process is happening in these cells, that means the amount of the substance is depositing over the cathode and liberating from the anode, right? So from the cathode the substance is depositing, and from the anode the substance is liberating, going out from the anode. Okay, similarly happens from here, in the second cell, in the third cell too. Okay, so in both these cells, in all three cells, same thing is happening, and also same quantity of electricity is passing through several electrolytes, that means through these electrolytes. Then what are we saying? That mass of substances which is deposited over the cathode. So let's suppose here the mass deposited over cathode is m1 for the first cell, here the mass deposited is m2, and here the mass deposited is m3. So the mass of the substance deposited are proportional to their respective chemical equivalent or equivalent weight. Okay, that means here in the first cell case, the M1 will be proportional to its respective equivalent weight. Okay, and similarly in the case of cell 2, that M2 is directly proportional to its respective equivalent weight. Similarly in the case of M3, that mass of the deposited electrolyte, okay, is directly proportional to the equivalent weight of the substance. Okay, so this is what the Faraday's second law is saying. Okay, so these are the two statements where W equals to the mass of the substance, E equals to the equivalent weight of the substance. Okay, here we are using W as the representation of the mass of the substance. E we use as the equivalent weight of the substance. To determine or to depicting the equivalent weight of substance, we use capital E. Mathematically it can be represented as follows, that the mass of substance is directly proportional to the equivalent weight of the substance, right? Mathematically you can write it as per the definition given by the Faraday's second law, that the mass of a substance deposited at any electrode on passing a certain amount of charge is directly proportional to its chemical equivalent weight, which we are representing here by the capital E. Also, the Z equals to E by F. Equivalent weight equals to atomic weight upon valency. This is the formula for the equivalent weight. That means E. Equivalent weight is atomic weight of the substance divided by the valency of the substance. So it can also be expressed as W1 by W2 equals to E1 by E2, because the mass, W is the mass of the substance deposited is directly proportional to the equivalent weight of the substance. That means the W1 by W2 is equals to E1 by E2. You can say this in the ratios, right? So this is the formulation or mathematical representation. Now let's more talk about the Faraday's second law. So illustration of Faraday's second law. Consider three different chemical reactions which is occurring in the three separate electrolytic cells. Okay, now again we are considering here three separate electrolytic cells. Okay, so this is solutions of the electrolyte. These are the two dipped electrodes connecting with the wires. Okay, so they are connecting with the wires. Okay, so what we are saying that consider the three different chemical reactions occurring in the three separate. Let's suppose this is the first cell, this is the second cell, and this is the third cell. Okay, now there are three separate electrolytic cells through which the chemical reactions is happening or occurring. which are connected in the series. Now they are connected in the series. These three cells are connected in series. In series means, as you have studied in the physics, when you say that resistance in the series, so series means they are connecting in the same wire, through the same wire. In the parallel means that they are connecting in the parallel wire, right? These are the connection made in the parallel, and this is the connection made in the series. So we are considering here three different cells, electrolytic cells, in which the chemical reaction is occurring, and the cell are connecting in the series. In the first electrolytic cell, the following reaction occurs. So what is the reaction? It is sodium positive plus 1 electron will give you sodium in a solid state, in a metal form. Okay. And in the second electrolytic cell, the following reaction is occurring. Copper 2 plus 2 electrons will give you copper. Okay, so this is the sodium reaction of the reduction process which is happening in the first electrolytic cell. In the second electrolytic cell, this is the reduction process of copper 2 positive ions which is happening on the in our cell, in our second cell, right? Similarly, in our third cell, the electrolytic or the in our third electrolytic cell, the following reactions occurs. You can see we have aluminium reduction reaction. That means aluminium will give 3 number of electrons and become aluminium in the neutral form. Okay. When supposing Y moles of the electrons are passed, the mass of the sodium, aluminium and copper liberated are 23 Y grams, 9 Y grams and 31.75 Y grams respectively. Okay, so what we are just here illustrating the Faraday's second law. Okay, and if we again repeat that what was the Faraday's second law, it was that mass, that means the mass of the substance which is depositing over the electrode in the cell reaction, right? That is directly proportional to our Q, right? And Q is equals to IT. So M is given as ZIT in our first law, right? And also we are saying in our second Faraday's second law, that the mass of the mass of the substance which is depositing over the electrode is depending on the charge. Now here we are taking three different cells which are connecting in the series. Okay, and they are having different chemical reactions. Their chemical reactions is also given. In the first electrolytic cell, this is the reaction happening, which is the sodium reaction happening, right? So, and in the second cell, you can see the happening of the reaction is the copper. And if you observe in all the three cells, the reduction process is happening and only the half cells are given, right? So, what we do in the third electrolytic cell, the reaction happening is for the aluminium, right? Now we are saying that when you are supposing that Y number of moles of electrons are passed through our cell, as I said that the cell are connected in the series. That means series means in the same wire, right? In the same wire. So that means same amount of the electrons are passing through the one point and ending to the second point, passing through three of the cells. Like let's suppose this is the first cell, this is the second cell, and this is the third cell, and they are connecting in the series. Then if you start to flow some amount of electrons through this first cell, then it will end at the third cell directly because they are connecting in the series. So we are supposing here that let's suppose we have Y moles of electrons, okay, and they are passing through the cells. Then the mass of the sodium is happening, or sodium is present in our first electrolytic cell. So the mass of the sodium, in the second electrolytic cell we have copper, and the third electrolytic cell we have aluminium. So the mass of the sodium, aluminium and the copper which are liberated, okay, which are deposited or liberated, because it is the reduction process, okay. So the mass which is liberated for the sodium, aluminum, and copper is 23Y for the sodium. That means 23 is the mass of the, you can say, atomic mass of the sodium multiplied by the number of moles of electrons, which is Y, right? So, because this is the illustration of Faraday's second law, which says that the amount of different substance which is liberated by the same quantity of electricity which is passing through the electrolytic solution are proportional to their chemical equivalent weight, right? Or you can say atomic mass of the metal divided by the number of electrons required to reduce the cation. So basically, the Faraday's second law says that whatever the mass is deposited or liberating at the electrode, the mass is directly proportional to the equivalent weight of the substance, right? And equivalent weight is the atomic mass of the substance, whatever the metal is, and whatever the electrode we are talking about. So the metal which is depositing or deliberating through that electrode or on that electrode, its atomic mass. How can you find the equivalent weight of that electrode? So the atomic mass divided by the number of electrons which are required to reduce the cation. Okay, that means whatever the number of electrons it is gaining or losing, okay, that will come in the denominator. So this is how equivalent weight will be defined, and that equivalent weight decides the mass which will deposit or liberate from our electrode. So if we are giving three cells where sodium, copper, and aluminium reactions are happening on the electrode, and we are supposing that Y moles of electrons are passing, then the mass of the sodium, the aluminium, and the copper which is liberated, that means mass is directly proportional to equivalent weight. Equivalent weight is atomic mass divided by the number of electrons, right? So the equivalent weight will be 23Y. So for sodium, the mass is 23. So the equivalent weight, the mass of the sodium will be 23Y. For aluminium, it is 9Y. For the copper, it is 31.75Y grams respectively. So these are the masses of the liberation at the particular electrode according to the Faraday's second law. Okay, so this is the example we have take, in which we have take three cells having different reactions occurring at the electrode. In the first one we have sodium reaction, in the second one we have copper reaction, in the third one we have aluminium reaction. And then we are supposing that Y moles of electrons are passing through the cell. Then the mass of the sodium, aluminium, and the copper which are liberated are 23Y grams for sodium, 9Y for the aluminium, and the 31.75Y for the copper. Okay. Okay. Now let's do the example, which is marked as example 2.10 in our NCERT textbook. The example says that a solution of the copper sulfate is electrolyzed for 10 minutes with a current of 1.5 ampere. What is the mass of the copper which is deposited at the cathode? Okay, so it is saying that we have a solution of copper sulfate, okay, and we are electrolyzing it for the 10 minutes of time. Like T will be 10 minute, we will convert it into the seconds, and the current is 1.5 amperes. You have to tell that what is the mass of the copper which is deposited at the cathode. Okay, so what I was explaining you, then we can again explain it, or we can use that to solve this question. Okay, so let's see. So let's try to solve it. So we have given the, first of all we will see what is given. The given amount is the time for which the current is passing, for which the electrolysis is happening, which is 600 seconds. How it is it? So basically we have given the 10 minutes time, right? So if you know 1 minute have 60 seconds, then 10 minute can have 10 times 6, 10 times 60 means 600 seconds, right? So similarly we have written that time is given as 600 seconds. Charge as we know, is current times current multiplied by time. Time we know, current we also know, which is 1.5 ampere. So we can definitely get the charge from this. So the charge will be equals to 1.5 ampere current multiplied by the 600 seconds. So, okay, while applying these formulas, you have to consider the units, because whatever the unit is given in our question, that can be different, but you have to convert that unit in the standard unit which we use to apply our formula. Okay, so that's why we convert the minutes to the seconds, because in our formula we use the time in seconds. So here we convert the time from minutes to the seconds. Charge will be current times time, and it will be 1.5 times 600 second, and this multiplication gives 900 coulomb as charge. Coulomb, C is representing coulomb, which is the unit of charge. So according to the reaction, okay, now what is the reaction of electrolysis happening for the copper sulfate, that you have to write here. And also the question asks that what is the mass of copper which is deposited at the cathode. So the reaction is copper 2 plus 2 electrons, giving us copper. Okay, in the copper we are adding 2 electrons and getting copper in the neutral form in the solid state. So this is the cathode reaction first of all, and we will require 2 Faraday or 2 times 96487 coulomb to deposit 1 mole or 63 gram of copper. Why we are saying that? Because 1 mole of copper, to get 1 mole of copper, we need 2 electrons, or the quantity of electricity which we will going to use is 2 Faradays, or 2 times 96487, the value of Faraday we just put here. Sometimes we also take the standard one, 96000, which is, which we use to make the solution or make the calculation easy. So you can also consider that. So 2 times the Faraday to deposit 1 mole or 63 gram. In the 1 mole, the amount of the copper is 63 gram. That's why we are writing here as 63 gram of copper. So for the 900 coulomb, so we are, again apply here the unit conversion thing. So for deposit, for the 1 mole or the 63 gram of copper, we require 2 Faraday of coulomb of charge. Now for 900 coulomb of charge, the mass of copper that will be deposited will be, so how you can find it? So we know, first of all, we apply the unity method. Okay, so we know that we require 2 Faraday charge to deposit for 1 mole of copper, right? Or you can say 63 gram of copper. Okay, now for 1 Faraday, that means that we will require 1 Faraday of charge to deposit the half mole of copper, you can say that, or you can say 63 by 2 gram of copper, right? Now for 900 coulomb of charge, what will be the mass of the copper that will be deposited? We will just multiply this 900. So 63 by 2 multiplied by 900 grams will be the mass of the copper. Okay, and also we are taking here in the form of coulomb. Okay, so we have to consider the F as this much, 96487. Okay, this is 2F, here 2F. So you have to take here as 63 divided by 2 multiply by 96487 multiply by 900 gram of copper. So this is the whole weight. So the copper mass that will be deposited is 63 multiplied by 900 divided by 2 times 96487. Okay, 2 Faraday. Coulomb mole inverse. So you just have to divide this fraction after this multiplication present in the numerator and the denominator, and you will get it equal to 0.2938 grams. So the copper that will be deposited for the 900 coulomb will be 0.2938 gram. Okay, and that will be the answer, because as the question asks that what is the mass of the copper that will be deposited. So mass of the copper deposited is 0.2938 grams. Now let's talk about the products of electrolysis. This is the subsection marked as 2.5.1. Product of electrolysis depends upon the nature of the material which is being electrolyzed and the type of electrodes which we are using. If the electrode is inert, that means, for example, platinum or gold, it does not participate in the chemical reaction, that means it will not react. The products of the electrolysis will depend upon different oxidizing and the reducing species which are present in the electrolytic cell and their standard reduction potentials. For example, we have at the cathode, there is a competition between the following reduction reactions. This is the first reaction, sodium ion gaining one electron becomes sodium neutral. The standard reduction potential for this is minus 2.71 volt. Okay, this is the first reaction. The another reaction which is competing for the cathode is H positive gaining an electron and becoming half of H2 in the gaseous state. The standard reduction potential for this is 0, because if you see in the electrochemical series given in our NCERT textbook in this chapter, the standard reduction potential for this reaction of hydrogen is 0. Okay, so these are the two reactions which are competing for happening at the cathode electrode. Now, what will be the reaction that will actually happen at cathode? So, the reaction with higher value of E0, standard reduction potential, is preferred because it will be having the higher E0 value. That means it will be more preferred at the cathode, because at the cathode reduction will happen, right? So, therefore, the reaction at the cathode during the electrolysis is this hydrogen one, which is H positive plus electron giving us half of H2. Okay, this is the NCERT equation marked as 2.33. But H positive aqueous is produced by the dissociation of H2O, because H positive is an ion and it will produce by the dissociation of H2O molecule. That is H2O when dissociated into H plus and OH minus, then we will get the H plus. Okay, this is the equation marked as 2.34 in the NCERT. Therefore, the net reaction at the cathode may be written as sum of 2.33, that means this equation, and 2.34, that means this equation. Okay, so the net reaction at the cathode, because the net reaction should happen, is this one for the H positive. But H positive we are gaining from H2O, the dissociation of water, which is H plus plus OH minus. Therefore, the net reaction which will happen at the cathode can be the sum of 2.33 and 2.34 equation. So we have H2O plus electron, because this H positive will cancel out, half of H2 plus OH minus. Okay, this is the NCERT equation 2.35. Now, what will be the reaction at the anode? At the anode, following oxidation reaction are possible, which is chlorine, in which the chlorine is dissociating into half of Cl2 plus losing one electron. The standard potential for this cell is 1.36 volt. This is the equation 2.36 in our NCERT textbook. The another reaction is 2H2O giving us O2 plus 4 of ions of proton plus 4 electrons. Okay, the standard potential for this reaction is 1.23 volt, and this is the equation which is marked as 2.37. So these are the two reactions which can happen at the anode. Now, the reaction at the anode with the lower value of E0 is preferred. Okay, so the opposite will happen. At the anode, oxidation happens, so whatever the value of E0 is lesser for which reaction, that will be preferred at the anode, and therefore water should get oxidized in the preference to chlorine. Okay, because it is having the lesser E0 value. However, on the account of overpotential of oxygen, the reaction 2.36 is preferred, because this oxygen is having the overpotential. That's why this reaction 1.36 we prefer. Finally, the net reaction, the net reaction NaCl in the presence of water giving us sodium positive plus chlorine negative will be having the cathode reaction as H2O plus electron giving us half of H2 plus OH minus, and the anode reaction as chlorine, giving us half of Cl2 plus 1 electron. Okay, so this is the cathode and anode reaction finally. Thus, the net reaction will become NaCl plus water, giving us Na positive, this one, plus OH minus, plus half of H2 and plus half of Cl2. Others will cancel out, that this electron will cancel out, this chlorine negative will cancel out. So this will be the final net reaction on the basis of standard electrode potentials of the reactions of the electrode, right? And that will decide the net reaction. So this is how we can decide the products of electrolysis. Okay, so thank you very much for attending this session.